Okay, in this video, I'm going to be giving a quick overview of the basic postulates of quantum theory, as well as a brief introduction to Dirac or Bra-Ket notation, which is a notation commonly encountered when dealing with linear algebraic manipulations in quantum calculations. Starting off with postulate 1, we have that any physically measurable property of the system is represented by an hermitian operator. Looking at the first equation, we see that it's expressed with angle brackets. So we have angle bracket F, and then a vertical line, and big G and little g with another angle bracket, for example. If we look at equation 2 and we remove big G from equation 1, just the left side we're talking about, we see that the angle bracket notation is a shorthand notation for the integral on the right side of equation 2, which is the integral of the complex conjugate of f with the asterisk denoting the complex conjugate of f multiplied by g d tau. So putting these two together, we look at equation 3. And so for an example, we have an hermitian operator satisfies the condition in equation 3, which is the integral of the complex conjugate of f times big G operating on little g d tau is equal to the integral of big G operating on f, then with an asterisk outside of the parentheses denoting the complex conjugate, multiplied by little g d tau. So on top of that, we have another theorem that goes along with hermitian operators, and this is stating that all eigenvalues of an hermitian operator are real. And the motivation here is that physically measurable properties are measured in real numbers. Okay, in our departure from classical physics to quantum physics, we have postulate 2, which states that properties from classical physics in terms of spatial coordinates and momentum are going to be expressed in terms of quantum mechanical operators. And here in equations 4 to 6, we see the momentum operators, which are differential operators. So starting with what you would expect from classical physics, we have px, and then the quantum mechanical version is px with a hat over it. So px hat equals h bar over I d dx. And then you have the same for py and pz. Although I'm not going to provide a proof for the fact that the momentum operator is going to be Hermitian, going from postulate 1, you can expect physical observables in quantum mechanics to be Hermitian. Going on to postulate 3, we have that the most complete description of any bound state of a physical system is given by a function psi in a Hilbert space for that system. So the psi is the wave function. And in general, we're looking for a description, a mathematical description of the quantum state of a particle. So the psi, or wave function here, is going to give, it's a mathematical function that is going to give the most complete description of any bound state of the physical system when we're dealing with quantum mechanics here and quantum states. I'll probably make another video to describe Hilbert spaces in more detail, but for this video, we can say that a Hilbert space is an abstract vector space or generalized vector space. So maybe you have a two-dimensional Euclidean plane or three-dimensional space, two-dimensional space or three-dimensional space that you're familiar with from physics so far. And a Hilbert space generalizes this idea. Noting another theorem dealing with Hermitian operators, we can say that the eigenvectors of an Hermitian operator form a basis for a Hilbert space. This tells us we can construct a basis from eigenfunctions of any Hermitian operator on the Hilbert space. So say we take capital G hat as an operator corresponding to some physical observable G, then all possible values of G are given by the various eigenvalues of the operator capital G hat. Expressing this more formally, let the set psi subscript k be an orthonormal set of eigenfunctions such that the operator G hat, capital G hat, psi subscript k is equal to lowercase g subscript k psi k. And remember, we've said that the eigenvectors of an hermitian operator, so the hermitian operator would be an operator that is corresponding to a physical observable. So the eigenvectors can form a basis for a Hilbert space. And this set is a basis, as we've said, and the wave function of any state of the system can be written as a linear combination. We can write the linear combination as is written in equation 8. So we have psi is equal to sum of a subscript k multiplied by psi subscript k for all k's. Now we're going to go back to what we were talking about in the beginning of the video, and we're going to reintroduce the Dirac notation, or the angle bracket notation, otherwise known as Dirac notation. So in Dirac notation, the eigenfunctions are written with the ket vector. So when the angle brackets are written this way, we have a ket vector. And in equation 9, we have the operator. So G, capital G hat, times ket k is equal to lowercase g subscript k multiplied by the ket vector k. And now we can say that the complex conjugate of ket vector k is written with the angle brackets facing the other direction, which is the bra. And with wave functions, we have the wave functions are written psi, and the ket vectors are written with the angle brackets facing the one way, and then the complex conjugate, so psi with an asterisk, are written with a bra. So the complex conjugate is written as a bra vector, while the other is written as a ket vector. And the inner product of the two wave functions we have here, psi a and psi b, make a bracket. So we have the ket vector and the bra vector. Combining the two makes a bracket. And we are talking about orthonormal eigenfunctions. So we have a relation about orthonormal eigenfunctions in equation 10, and that relation is bra j ket k equals delta j comma k. And the norm of psi is equation 11, which is in brackets we have psi in brackets, so bra psi ket psi is equal to, for all values j and k, the sum of the complex conjugate of a subscript j multiplied by a subscript k, which are the coefficients, and then ket k bra j equal to the sum of a subscript k multiplied by the complex conjugate of a subscript k for all values k. And here we've used the Kronecker delta. So the delta in equation 10, delta jk, is equal to 0 if j doesn't equal k. But if j is equal to k, then that delta jk is equal to 1. Now we're moving on to postulate 4. Postulate 4 states that if you consider an arbitrary state represented by a normalized wave function that is subjected to a measurement with a property g corresponding to an operator capital G hat, let g subscript k be the eigenvalues of capital G hat, and let ket k be orthonormal eigenfunctions that span the Hilbert space. The result will be one of the eigenvalues g subscript k, and the probability of getting a particular g subscript k is the complex conjugate of a subscript k multiplied by a subscript k, where a subscript k is equal to bra k ket psi. Now if you go back to equation 8, where we said that the set of orthonormal eigenfunctions that form a basis for the Hilbert space and the wave function of any state of the system can be written as a linear combination, we have that psi is equal to the sum of a subscript k multiplied by psi k. And the coefficients can be thought of as projections of the wave functions onto the eigenfunctions of the operator, or the basis functions. Or you can think of this value from the sum in equation 8 as the degree to which the full wave function possesses the character of a single eigenfunction, or a single psi subscript k. Now, if we want to express postulate 4 symbolically, let's say we have a large number of identical systems, each of which is described by a given wave function, so a given psi. And we have that each of these are subjected to a measurement of g. The average result, or expectation value, is a sum of possible outcomes weighted by their individual probabilities. Or we can express this here in equation 14 as the sum of the complex conjugate of a subscript k times a subscript k times gk. And since gk is a value representing the eigenvalue k of the operator capital G hat, we can use the relations in equation 15 and 16 to say that the sum of the complex conjugate of a subscript j times a subscript k times g subscript k, bra j cat k, for all values jk, is equal to the sum of the complex conjugate of ak times gk, for all values k. In other words, we can conclude by expressing the expectation value with two sides in a bracket being operated on by the operator capital G hat.